Good afternoon, everyone. Good morning. I think it's afternoon where most people are. And welcome to the third ZeroPM webinar. And actually, this is our first webinar for 2024. So for those of you who don't know me, my name is Sarah Hale. I work for the German Water Centre. And for those of you who don't know ZeroPM, which is why we're here, it's a Horizon 2020 project where we're looking at interlinking prevention, prioritisation and removal strategies to protect the environment and human health from persistent and mobile substances. So what we have today is a very exciting webinar where we're going to hear from two speakers, two people that work in ZeroPM. The first is Michalis Fountoulakis, and I've practiced his name, but I know it's not perfect. He has a PhD in chemical engineering from the University of Patras in Greece, and he's working now at the University of the Aegean, where he's an assistant professor of environmental biotechnology. And Michalis works a lot with anaerobic biodigestion of waste and wastewater. The second speaker that we've got today is Marcel Riegel, and he works at the same place as I do, at the German Water Centre. He is working to provide science-based consulting to drinking water suppliers related to all aspects of drinking water treatment. Within ZeroPM, Marcel leads the work package that's related to technical solutions. And this is a work package that aims to investigate if and how these legacy persistent and mobile substances can be removed from water and sludge. So what we're going to be hearing about today is the work that we do in ZeroPM related to treatment of water and sewage sludge. So I think with that, I am going to hand over to Michalis and he can start his presentation. If anybody has any questions during the presentation, please put them in the question and answer box. Hans-Peter is going to be looking at the box and going through the questions at the end. And I think if you are set, Michalis, you can take over from me.
Okay, thank you, Sarah. Okay, first of all, I would like to thank you.
We'll just pop it in presentation mode, Michalis. Just pop it into presentation mode. No, it's okay.
Firstly, I would like to thank you all for your participation in this webinar. I will try to share our experience, our findings regarding the fate of PFAS during anaerobic digestion of sewage sludge, with the addition of carbon-based conductive material, specifically the granular activated carbon. As you may already know, sewage treatment plants serve as significant point sources for PFAS. These compounds end up in sewage treatment facilities from various channels, such as directly industrial discharges, from household products containing PFAS, such as textiles, cosmetics, or cookware, or even synthesized in situ from PFAS precursors. Now, inside a sewage treatment plant, PFAS are very stable, non-biodegradable compounds, so they are detected in final effluent as well as in sewage sludge. The majority of previous studies focused on the occurrence, on the fate of PFAS in treated wastewater, but from limited available data, we also know that PFAS are present in sewage sludge at various concentrations, range from 3 nanograms per gram in Africa to about more than 2 milligrams per gram in some studies in Europe or Asia. It seems from these studies that PFAS concentration increased in sewage sludge from in urban or industrial areas. So the issue from the presence of PFAS in sewage sludge is that in any case, in any option, PFAS could be released in the environment from even from reuse in agriculture, from incineration, or from landfills. So there is a potential risk for the environment and human health. For this reason, it is crucial to find an efficient treatment method of PFAS before the final disposal of sewage sludge. In this context, the anaerobic digestion process is a widely applied technology for the treatment of sewage sludge, as well as for many other organic waste or highly organic polluted wastewater. The main advantage of this bioprocess is the production of biogas. Biogas is a renewable energy source. However, there are some limitations in the process. As you can see the diagram, the complex organic matter is initially hydrolyzed into dissolved monomers. These compounds are then converted to volatile fatty acids and alcohols, and further transformed to hydrogen and acetate. The final step is performed by slow-growing methanogens, and it is assumed that methanogenesis is the rate-limiting step of the process. What is the problem? The problem is that the production of hydrogen from VFAs and alcohols is thermodynamically feasible only if the concentration of hydrogen is very, very low. This is achieved by the consumption of hydrogen by hydrogenotrophic methanogens. This process is known as hydrogen-mediated indirect interspecies electron transfer, and is assumed to be a bottleneck of the overall process. So a new concept to overcome this problem, this issue, is to promote direct interspecies electron transfer. How can we do this? There are two different options, as you can see this picture, by adding conductive materials or by applying external voltage. In this case, there is no need for electron carriers such as hydrogen, as the electrons produced from the biodegradation of organic matter can be directly captured and utilized by methanogens. In previous studies, different electrically conductive materials have been studied, carbon-based or metal-based, such as biochar activated carbon, graphite, or metal-based such as magnetite. Different values of applied voltage are reported from 0.2 to 1.5 volts, and electrodes used for the application of voltage was carbon rod, carbon brass, or carbon cloth. Interestingly, some studies focused on the promotion of diet process also reported enhanced removal of several organic micropollutants. So the objective of our study is to examine the individual and combined effect of a conductive material, granular activated carbon, and external volatile application on the anaerobic digestion of sewage sludge, mainly on methane production, but also on the removal of PFAS, specifically PFHPA, PFOA, PFNA, PFDA, PFUDA, and PFOS. Here you can see some information about the experimental conditions, the experimental data. 4 reactors were operated in parallel with a working volume of 1 liter. In the first one, we apply external voltage. In the second, external voltage and GAC addition. In the third, only GAC addition. And the fourth was operated as a typical anaerobic digester without the addition of any conductive material or the application of external voltage. The HRT was 20 days. The experiment was running at thermophilic conditions, 45 degrees. The concentration of GAC in the reactor was 10 grams per liter. The electrodes used for the application of voltage was carbon cloth. The voltage applied was 0.8 volt. And the examined PFAS were spiked in the reactor and in the feed at a concentration of 100 micrograms per liter. We monitored several parameters, such as pH, solids, organic matter, the intermediate products, volatile fatty acid, and of course, PFAS. And at the end of the experiment, we also analyzed the microbial communities established in the four reactors. Here you can see the results regarding the effect of GAC addition and voltage application in the reactors. As you can see with red and blue bars, reactors containing GAC had higher methane production, and also it seems that GAC enhanced the VS reduction as well as COD and VFAs consumption. We also noticed that the methane content in the anaerobic digester containing GAC was almost 60% higher compared to the typical anaerobic digester, which was around 50%. Here you can see the variation of VFAs in 4 reactors during the experiment. It is you can see that the VFAs concentration in reactors containing GAC was lower than the other 2 reactors. So it seems that the addition of GAC promotes the methanogenesis steps. Of course, there are several potential mechanisms for this enhancement of methane production. Of course, GAC could promote the diet process, but also it is known that GAC is a porous material with large surface area and high absorption capacity. So GAC could promote the establishment of biofilm on its surface, not only electroactive bacteria, but also acetoplastic or hydrogenotrophic methanogens. And of course, GAC could also adsorb some toxic for the process compounds, such as ammonia, hydrogen, or VFAs. In this figure, you can see the distribution of PFAS between dissolved and solid phase in the influent and in the reactors. As you can see, PFAS with a smaller number of carbon atoms were mainly in liquid, in dissolved phase, while PFAS with an increased number of carbon atoms were mainly in solids. In addition, as you can see, the presence of sulfonic acid increases sorption, and comparing total PFOS and linear PFOS, we can say that branched PFOS have a higher solubility. Here is the results regarding the removal of PFAS in the digesters in the anaerobic reactors. As you can see, with green and purple color, reactors with GAC achieved a notable removal of PFAS, while in the other two reactors there is no removal of any of examined PFAS. And comparing this figure and this figure, we can say that the PFAS in the dissolved phase removed in higher rate. So it seems that dissolved PFAS are more bioavailable to microorganisms. We say microorganisms that it seems that biotransformation is the main mechanism for PFAS removal in the systems, because we measure PFAS both in the dissolved and particulate phases, and it is known that PFAS are not volatilized or hydrolyzed at 55 degrees. So in addition, there are some recent studies reporting this observation that that PFAS can be biotransformed under anaerobic conditions. This statement is also supported by the findings from microbial community analysis. As you can see in this figure, with the blue color is the Copro-Thermobacter, which are dominant in all reactors. But you can see that in reactors containing GAC, there is an increase, a notable increase of these three types of bacteria: Acinetobacter, Pseudomonas, and Bacillus. Acinetobacter is this with a red color, Pseudomonas is this wine color, and Bacillus is this brown slashes. So there is no significant amount of Acinetobacter in other two reactors, but only in the reactors containing GAC, and similar with the other two bacteria. So we know that Copro-Thermobacter is a very common hydrogen-producing bacteria identified in anaerobic thermophilic reactors creating sewage sludge from several studies. And we have some evidence that these three types of bacteria could be related with the biotransformation of PFAS. Why? Because it is known that these bacteria increased in GAC supplemented anaerobic digesters. It is also found in PFAS contaminated matrices, soil, water, and is related with their possible biodegradation. And it is also known that they are effective for the biodegradation of other organic micropollutants, such as phenols, benzene, toluene, trifluoroethylene, etc. So in conclusion, we can say that GAC addition increase methane production during anaerobic digestion of sewage sludge. In contrast, the application of external voltage had no effect on the process. The addition of GAC not only increased methane production, but also enhanced the removal of PFAS, of 4 out of 6 examined PFAS, and this removal is related to their presence in the dissolved phase. And of course, the presence of these 3 bacteria, and especially Acinetobacter, may be related to the biotransformation of PFAS. In the near future, we are planning to conduct some experiments, similar experiment, but at pilot scale, with GAC addition and external bottle application. In this photo, you can see the pilot plan. We will use as feed secondary treated sewage sludge, and we are planning to apply also ultrasound or thermal pretreatment. Thank you very much for your attention.
Thank you, Michalis. That was great. So now, Marcel, we can move on to the second half of the presentation. So if you just want to bring up your slides. And for anybody who has any questions, just pop them in the question and answer. Michalis, there is a question in there, so you could just go in and answer if you'd like to. That looks really good, Marcel. Perfect. Then I'll hand over to you.
Okay, thanks, Sarah, for the introduction. Welcome, everybody, to the second part of our today's ZeroPM webinar. And we now switch from the wastewater and the wastewater sludge part to the drinking water part. And I'm going to talk about the removal of PFAS out of drinking water and the work we do on this topic within our ZeroPM project. Because the group of people in this webinar is quite big, I wanted to start with a short introduction about PFAS itself. So PFAS is not a single substance. PFAS is a very, very huge substance group. And as first number here, I have that it's more than 5,000 substances, which is a quite old number. So the newest number I know from ZeroPM partners, they say it's more than 7,000 different substances, which are called as PFAS. So it's a really huge substance group, but there's one thing that all these PFAS substances have in common, and that is that one part of this PFAS molecule exists of a carbon chain which is fully fluorinated or partly fluorinated. So the hydrogen atoms, which are normally at the carbon structure of this molecules, they are replaced by fluorines, and this is the on the left-hand side, the part of this molecule. On the other side, which is shown here as blue part, there is one part of the molecule which is not fluorinated, and this could be nearly everything what you can find in chemistry. As examples, this could be a sulfonic acid and a carboxylic acid. These are substances we could directly measure and find in our analytical labs, but this part of the molecule could be everything, like it is shown here, the two examples at the bottom. And this non-fluorinated part of these molecules, this is not so stable as this fluorinated part, and this non-fluorinated part could be degraded in nature to this stable end substances like this sulfonic acids or this carboxylic acids. And because of this, these substances are called precursors. Because there are substances which could be degraded to these other end substances. What is important for drinking water or for drinking water suppliers? It is important that we will have some new drinking water threshold values in the future. So based on a regulation from the European Drinking Water Directive, there will be a new drinking water threshold value, which is called the sum of 20 different PFAS. And this is a sum of 20 single substances, and these 20 substances are 10 carboxylic acid and 10 sulfonic acids, and each of them with chain numbers between 4 C atoms and 13 C atoms. And the sum of these 20 substances, they are in the future are not allowed to extend the value of 0.1 micrograms per liter. And this is a European directive, so each European member country has to implement this threshold value into their national laws in the future. On this table here, you could see a list of different substances, and I wanted to show what is the nomenclature of this single PFAS. So there's one letter in all of these names which is underlined, and this part of this name shows the chain length of the single PFAS. So in the example here in the table, which is on the really top, which is PFBA, this B stands for Bhutan, which means it's a chain length of 4 C atoms. And the whole name of PFBA, you could see that, yeah, the B stands for the chain length, and this is the nomenclature of the single PFAS. Next to this drinking water threshold value, there will be another threshold value, which is called the sum of 4 PFAS. This is nearly the same from the idea like the sum of 20 PFAS. So the sum of 4 specific PFAS, which are counted in red color here, the concentration of these substances are summed together, and the sum of this concentration is not allowed to extend a specific value. The basis of this new value is not from the European Drinking Water Directive, but it is from the European Food Safety Authority, and they did a risk analysis of these 4 substances, and they brought out a value of a maximum mass intake of this 4 PFAS, which should not extend it. And if this maximum intake is calculated into a drinking water threshold value, you will get a value of 2 nanograms per liter for the sum of these 4 values of this 4 PFAS. And I have some examples here on the left-hand side from different countries which implemented threshold value for this sum of 4 PFAS. And as you could see, Denmark, for example, they already included such a value with a concentration of 2 nanograms per liter. There are other countries like Sweden and Belgium. They implemented a value of 4 nanograms per liter for the sum of these 4 substances, where they implemented a factor of 2 to that this value is not so low and not so difficult to hold. And there's another example in Germany. There will be implemented a value of 20 nanograms per liter for the sum of these 4 substances. But in general, these concentrations, like 2 nanograms per liter or 20 nanograms per liter, they are very, very low. So if you compare them to other threshold values of organic compounds, it's very low. And for the drinking water treatment, it's a really big challenge to reach these very low values. So general in drinking water treatment, if you would like to remove any organic micropollutants, you normally use ozonation or you use activated carbon. The problem is if you have very mobile substances like short-chain PFAS are, they are very poorly adsorbable. And then if you use activated carbon, this the lifetime or the operating time of this activated carbon is not very long. And then this activated carbon material has to be replaced after a very short period of time. And this leads to high treatment costs and to a very big operating effort that this material has to be changed very often. And therefore, new treatment approaches are tested with the goal to have a new treatment which is cheaper and which could be operated with less effort of manpower. And within this project ZeroPM, we are testing 2 different approaches. And one approach is that we test the combination of an activated carbon filtration and an ion exchanger filtration. And this ion exchanger filtration, the second step, is not used as a single use that the ion exchanger will be replaced when it's exhausted, but it will be regenerated using caustic soda. And by this regeneration, these PFAS, which are adsorbed on the ion exchanger, they should be removed again from the ion exchanger, and then they are concentrated in a higher concentration in a smaller amount of volume of regenerate. And after this regeneration, this PFAS should be destroyed in this small volume of water with a high energy destruction process, like, for instance, electrochemical degradation. The idea of firstly treat the water with an activated carbon and then with an ion exchanger is that if you have long chain PFAS which are adsorbed on the ion exchanger, it's not possible to remove them again while a regeneration where you only use sodium hydroxide. And therefore, we wanted to treat the water with this two-step approach, first activated carbon and afterwards ion exchanger, including regeneration. Yes. So when we started these investigations, we did a lot of lab experiments and tested different ion exchangers, and we checked how good can they adsorb PFAS and how good could these PFAS desorbed again with different regeneration chemicals. And as a result of these lab experiments, we used different ion exchangers, which we tested afterwards in the pilot plant in a waterwork. And we choose in general 3 different ion exchangers and tested them in the pilot plant. And in this waterworks, we built up a pilot plant with 3 different streets. And the first street was a single activated carbon filtration, which is our standard treatment where we have to compare all our other results with. And the second street was an ion exchanger, which we did not regenerate. So we used this ion exchanger in a single use, and we used a PFAS-specific ion exchanger for this treatment street. And the third treatment street was our combined treatment approach with first an activated carbon filtration and afterwards an ion exchanger, which was regenerated regularly. And on the right-hand side, you see the PFAS contamination in the waterworks, which we found in the groundwater. And there you could see that we have short-chain PFAS like PFBA and PFPEA in concentrations of up to 0.1 micrograms per liter. And we also have ultra-short PFAS like TFA or PFPRA, but these ultra-short PFAS, they are not relevant for the drinking water directives because they are not part of the sum of 20 PFAS. On the next 2 slides, you see some photos of our pilot plant. On this photo, you see 2 big activated carbon columns, which have a height of about 2 meters. So this is not a little lab plant, but it's a little bit bigger if you build something like this in the waterworks to be able to make an upscaling more easily. You normally use this bigger plants if you test activated carbon. And in between these 2 big activated carbon columns, you see a small ion exchanger column, which has a filter height of only 1 meter. Yes, because if you investigate ion exchangers, upscaling is much easier, and then you could use smaller columns for investigating these ion exchangers. And the technical frame conditions are listed on this slide here, but I don't want to talk about this in more detail. On this slide, you see on the left-hand side the 2 ion exchanger columns which are regenerated. So you see some extra pumps on this photo here, which we needed for this regular regeneration with sodium hydroxide. Now I wanted to show you some results we performed so far. On the left-hand side, you see the effluent concentration of the activated carbon filter. If we have a look only at the activated carbon, and here you see the breakthrough of the single PFAS which are found in the raw water. So the first breakthrough is observed for the short chain PFAS PFBA, which breaks through after a specific water throughput of about 5,000 bed volumes. At the throughput of about 10 to 15,000 bed volumes, the next PFAS with a chain length of 5 C atoms, PFPEA, breaks through. And after this, you could see breakthrough of PFHXA and afterwards of PFOA. So as longer the chain length of this PFAS is, as later the breakthrough into the activated carbon filter occurs. And if we detect the amount of water we could treat by this treatment technique, we could calculate our material costs, which we have to pay for, for example, activated carbon when we have to replace the activated carbon after a specific throughput of, for example, 5,000 bed volumes if we have to remove PFBA. So on the right-hand side, you see the breakthrough curve of this PFAS-specific ion exchanger, which is used for a single mode. And you could see here that the operating time or the water throughput through this column until the single PFAS substances break through is much longer. So for example, for the breakthrough of PFBA occurs at a throughput of 10,000 bed volumes, which is nearly twice as much as if you use the activated carbon. And from this breakthrough curves, we could calculate now our specific material costs, which are shown on the next slide. And this is depending on the substance which you have to remove. So if you have PFBA in your raw water in a concentration which is relevant for the new drinking water threshold value and you have to remove it, then your operating time using activated carbon is about 6,000 bed volumes, and then you have to replace the activated carbon by a new material or reactivated material. And if you use a price for activated carbon of 1.2 euros per liter activated carbon, you will get a specific material cost of 20 cents per cubic meter of treated water. But if your raw water has no PFBA or only PFBA in a very low concentration, but it has PFPA in a relevant concentration, and this is the relevant substance which says, or which is relevant for the change of your activated carbon, then you could get an operation time of 12,000 bed volumes, and this leads to a lower specific material price, in this case of 10 cents per cubic meter. If you compare now the use of activated carbon and the use of an PFAS-specific ion exchanger, then you see that the operating time for the different PFAS is much longer for the ion exchanger, but the ion exchanger is also much expensive if you buy them. We used a price of 9 euros per liter in this case, and if you calculate your specific material costs, they are much higher compared to the activated carbon treatment. So even if you can have a longer operation time with the ion exchanger, your specific material cost is higher than using only activated carbon. If we have a look for this treatment cost, if you have to remove PFBA and you could use activated carbon for an operation time of 6,000 bed volumes, and you will have to pay 20 cents per cubic meter of treated water. What will this mean in practice? For the people who have to pay this drinking water, this will mean that a 4-person household has to pay about 35 euros per year, which is, you could decide if this is a lot of money or if it's not. It is something, but I think most of the families could handle such an amount of water. But if you have a look what the water supplier has to pay for the treatment, if you take an example of a city which has to supply 100,000 people with drinking water, this will mean that the water supplier has to pay each year more than 800,000 euros for replacing activated carbon when it is exhausted. So this, for the cost which a water supplier has, is really high if you take this amount of 20 cents per cubic meter as the basic. And if you have your look what you have to pay for the remediation of your PFAS, so if your operating time is such low of 6,000 bed volumes, your specific remediation costs would be 400,000 euros per kilogram PFAS which you put out of the water. And this is a really high amount. If you have a look what is the price for PFAS, and then you have a look what you have to pay to remove it again out of the nature, these are really, really high costs. So now I want to show you some results of our combined treatment process. So where we first treat the water with activated carbon and afterwards with an ion exchanger which will be regenerated. So what you see on this slide is are the effluent concentrations of the single PFAS at the effluent of the activated carbon. And this is at the same time the influent of the ion exchanger as the second step. So you could see here the short chain PFBA is at a constant concentration of 0.3 microgram per liter, and after a throughput of some 1,000 bed volumes, your concentration of PFBA, PFPEA increases, and at later times also of PFHXA and of PFOA. And this is the inlet of the ion exchange resin. And okay, here I am. Here you could see the effluent concentration of the ion exchanger, and the dotted lines, the vertical lines, these are the times when we regenerated the ion exchanger. So we treated the ion exchanger with sodium hydroxide, and by this treatment we could remove the adsorbed PFAS out of the exchanger, and the exchanger was used again in a second circle. The gray lines are again the influent concentrations, and the red lines are the effluent concentrations of the single PFAS. And what you could see here, for example, between the first and the second regeneration is that we have PFAS which go inside the ion exchangers, but we don't have any PFBA or other PFAS which we can find at the outlet of the ion exchanger. If we increase the operating time and we regenerate after a period of 2 weeks, which is shown here, you could see that PFBA will be removed totally for the first week, and after 1 week, the concentrations at the effluent of the ion exchangers increases, and the ion exchanger can't remove the PFBA totally after this operation time of longer than 1 week. We have a treatment time at the right of this picture where we had operation time of 4 weeks, and at this time we could also see some of the PFPEA which we could find at the effluent, but in very, very low concentrations. So by this operation we could also remove the PFBA constantly out of the drinking water if we reduce the operation time of the ion exchanger of 1 week and don't exceed it to longer operation times. And if we try to evaluate this ion exchanger treatment, if we have an operation time of 1 week and after this week we regenerate the ion exchanger, then we will have a yield of 99%, which will mean that if we treat an amount of 100 liter of raw water, we will receive 99 liter of drinking water and only 1 liter of regenerate, where we have all of this short chain PFAS concentrated inside, and only this small amount of volume has to be treated with a further technology where we need high energy in principle to destroy this PFAS. But yeah, we could really concentrate the PFAS in a small amount of water. If you compare this with the treatment of a reverse osmosis membrane, this has normally a yield of 80%. And this will mean that the treatment of 100 liter will lead to 80 liters of treated water and 20 liters of PFAS containing concentrate, which has to be treated further. So the yield we could reach here by using this ion exchanger, including its regeneration, is very high, especially if you compare it to another technology like this reverse osmosis membrane treatment. So the next work we want to do is that we have to evaluate our ion exchange technology further on. So we could already say something about the efficiency of this treatment. So what is the yield we can achieve during this treatment and regeneration? What is the effectiveness? So what are the PFAS concentrations at the outlet of the ion exchanger, which will be found in the drinking water? And what we have to do now is that we make a cost evaluation about the treatment materials, the activated carbon, the ion exchangers, and also the chemicals we need for the reactivation, and have to compare these treatment costs to the single treatment of only activated carbon. So yeah, now I come to the conclusions. What I wanted to show you that in the drinking water treatment, we have the goal. No, we have the situation that we have new PFAS threshold values, and there are in general two values. One is the sum of 20 PFAS, which is very relevant if you have short chain PFAS in your raw water present, and this will and the other threshold value is the sum of 4 PFAS, which is only implemented in some European countries, but there are some countries which will implement this threshold value, and this value is very, very low in the single nanogram per liter concentration, so very low and very difficult to treat. So therefore, the existing methods we have in drinking water treatment, they are no longer well feasible to treat this or to reach these drinking water threshold values, and therefore new treatment technologies are needed. And we are investigating the approach of using ion exchangers, which we want to regenerate with sodium hydroxide. And so far, we provided that the proof of function has already been set, but now we have to evaluate if this technology is economical and is cheaper than if you only use activated carbon, which you have to replace in a short period of time. Yes, this is my last slide. If you have any question about this drinking water treatment, I would be very happy to discuss them with you. Thank you very much.
Great. Well, thank you very much, Marcel and Michalis. And there's been some very interesting questions being posed in the Q&A form, and I see Michalis has been doing an excellent job answering them and fielding them. And we have 10 minutes left, and we can maybe answer some of them online, and maybe I'll just go back and forth with a question from the first part on the sludge, and then on another one on the water treatment. And I might even also just go to a question that you already answered, Michalis, because it might be just interesting for you to elaborate. So one question was about on the chain length of PFAS. So reading the question from Asher Yearwood, I have a question for the GAC. Have you thought about how it is possible to apply GAC removal as well for longer PFAS chains, or more specific on to what chain length they may be effective? So maybe you can give your impressions on the role of chain length, Michalis, with your GAC approach to sludge.
Yes, as we see let's say the PFAS with small carbon atoms seems to have to be able to biodegrade, to biotransformed. But as the number of carbon atoms increased, the removal of PFAS is not possible.
Okay, but thanks, and it's definitely something we should have a closer look at going forward. So thanks for that question. And now I will maybe jump to a water question. Okay, so I'm just reading one about maybe more information on the ion exchanger. So now I'm reading a question from Sami Sofini Zarelli. What's special about the PFAS specific ion exchangers? What makes them PFAS specific?
I don't really know what is the chemistry behind this PFAS specific ion exchanger, but it's something with the side chain length that you have some steric interaction where this PFAS could dock more easily to the ion exchanger compared to sulfate, which has this 2 negative loads. So it's something about the side chain of the functional group of the ion exchanger, but I'm not really an expert in this.
Okay, no, thanks. Yeah, and I guess we'll, as we present results, we'll also give more information about the source of these ion exchange resins. And another question, this is relating to, I'd say, the mass balance of the PFAS. I'm trying to find it, but maybe you can just comment on it while I'm looking for the question. And that is, so I guess I'll first, maybe you can answer it on the sludge and then on the water, and that is, what do we know happens to these PFAS after they're reacted in the sludge, and how should we approach that? And then also over to Marcel, because the GAC technology and the ion exchange technology is more about removing the PFAS from the water, but what's the next step for destroying? Maybe you could comment more on how we can completely destroy these PFAS if that was our goal. Yeah. So Michalis first.
Yes, it is a nice question. We don't able to answer this question. Yes, we don't know if the PFAS are totally eliminated. We have to measure the free fluorine to see if PFAS are totally eliminated or not. We're planning to do this in future experiments.
Great. Thank you, Michalis. And maybe Marcel, you can maybe comment on some of the things you're working on.
Yeah, if you have a look on PFAS removal out of drinking water, so for example, activated carbon filtration is the first step. So you remove the PFAS out of the drinking water. The second step of the PFAS destruction is in the case of activated carbon, and thermal treatment. So you burn or you put it into an incinerating plant. So you burn the activated carbon or reactivate it thermally. And by this thermal treatment, the PFAS are destroyed. And if you have a kind of liquid-liquid separation process like this ion exchanger, including regeneration. So this is your removal technique. Then you have your PFAS in a smaller amount of water, and then you need a further destruction technique, which could be electrochemical degradation or others. But yeah, I presented the first step, but you have to have a look at the second step as well.
Great. No, thank you. And now back to, oh,
I'm
sorry,
Hans. We are also, I would like to, we are also planning to have another step after anaerobic digestion process in order to increase the elimination of PFAS. We are planning to apply hydrothermal carbonization as a post-treatment of anaerobic digestate. So maybe this also improve the elimination of PFAS.
Great, thanks. Yes, that'll be also very exciting to see. I'll just read a question. I guess this will go more into the mechanism of in the sludge and the under anaerobic digestion. So this is from Jano Johansson. Hi, did you run a control with GAC but no anaerobic digestion? If GAC is both continuously input and removed from the system and PFAS were not measured until 70 days, how do you know whether the GAC was taken out of the system or did not cause the PFAS removal? So I guess that's both a question of the effect of the conditions, aerobic and anaerobic, and also the role of absorption on the GAC.
The conditions is anaerobic conditions. We don't have aerobic conditions. Okay, and at the steady state of reactors, the amount of GAC in the reactor is constant. The amount of PFAS in the reactor added in the reactor is constant. So we can safely conclude that there is a PFAS removal in the effluent.
Mm-hmm.
We have a steady state conditions in the reactors.
Yeah. Yes, and also, and I'll just add, I think only like biodegradation of PFAS is only thermodynamically possible under anaerobic conditions through a reductive defluorination pathway. Yes. So a question to Marcel, I guess this is related to fouling. Does the activated carbon and ion exchange media react to other contaminants within the water and sludge? I presume this will affect the lifespan of the activated carbon, such as I guess for wastewater, reducing its potential significantly. Is this more of a polishing process for already low reduced concentrations of PFAS? Thanks. Very interesting talks. And that was from Andrew Oliver.
Yeah, the drinking water treatment, of course, you have competitors for the adsorption places of activated carbon, or if you have a high organic background matrix, a high DOC, this will affect the operation time of activated carbon. So the results I showed is at one specific case where we had a small amount of DOC of about 0.7 milligrams per liter. But of course, there are other effects like competitive effects or biofouling effects if you use activated carbon or ion exchange.
Mm-hmm. Oh, great. Oh, thanks. So I'll just try to find another sludge question first. Or maybe while I'm looking for that, I'll just ask something for both of you. When you talk about granulated activated carbon, it's a big thing about where this granulated activated carbon is sourced from, because this could have also an impact on the sustainability of the technology. Have you both given any thoughts into the source of the granulated activated carbon, whether it's biogenic or from anthracite? Maybe Michalis first.
Yes, Hans. I don't know if about the source of granular activated carbon. Maybe we can try other types of conductive materials, and we also have similar positive results, such as, for example, biochar, which is quite cheaper than granular activated carbon, or maybe some other conductive materials. Okay, we are also planning to test hydrochar produced during the hydrothermal carbonization as a material for to enhance the removal of PFAS. So we are planning to test maybe some other cheapest materials than GAC. The other option is to have a system to retain GAC inside the reactor in order to not have to add constantly GAC in the influent. This could be a membrane, an anaerobic membrane reactor, or an upflow anaerobic sludge blanket reactor. In that cases, we don't have release of GAC in the effluent.
Great, thank you. And Marcel.
The results I showed you, the breakthrough curves of the activated carbon filter, this was from a fossil charcoal. But in our pilot plant, we had these 2 columns of activated carbon, and the other column was filled with a coconut shell coal. So we tested both of them. And from the results I know, coconut shell is not so well feasible for PFAS elimination, except if you use a highly activated coconut shell activated carbon. And these ones are working quite well for PFAS removal.
Great. No, well, thank you very much. I see we're running out of time, and there's still maybe I see many interesting questions in the Q&A. And we will, I think, continue to have a look at this Q&A after this webinar is complete. And we might also reach out to some of the people who asked questions to provide answers after this webinar. But for now, I would like to thank you all for tuning in and joining us for this past hour as we learn of some of the remediation and removal technologies we're developing for PFAS and PMT substances in sludge and in water. And please stay tuned for future results. Our results will, as we post them, will be available following our social media channels, maybe also in another webinar. So please follow us at ZeroPM.eu and on our Twitter and LinkedIn. And for now, I'll just say thanks for joining us.
Thanks very much, everyone.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.